Hey, welcome everybody. Welcome to the first and hopefully only virtual version of our annual Day of Preparedness. Whereas we normally take over City Hall, which Ann and Lauren and myself are in right now, the only three people in the building. This year, instead of taking over City Hall for the weekend, we're taking over your Zoom channel. So my name is Scott James. I'm the founder and board chair of Bainbridge Prepares. We are super glad you are here with us today. A few logistical details. Let me pop open our slides for today. Everybody see those? All right. So all of our team leads are going to be joining us at 1 p.m. for a live Q&A with the entire community. You're welcome to submit your questions. And how do you want them to, just in the chat or via email? Okay, so pop them into your chat. So these are questions not necessarily for our scientists this morning because they're going to have Q&A sessions as well, although you're welcome to bring those at 1 p.m. But questions about Bainbridge Prepares in general or any of our specific teams and what they have going on. Related to that, you can find some new team videos that we posted this week at bainbridgeprepares.org/teams. Scroll to the bottom below the org chart and you will find all those new videos. For those of you who registered ahead of time, I'm looking at a table full of really cool gift bags. So Anne, how do you want them to pick them up this upcoming week? Oh, Anne emailed out a schedule already that I'm obviously behind in my inbox on how to and when to pick those gift bags up. So we will aim to have a few minutes between sessions today, but like for bio breaks, but you know, this is Zoom, so just turn off your camera and you'll be fine. So here's our agenda for today. Let's see, at 1 o'clock, let's go backwards. At 1 o'clock with the team leads, they're going to join our executive team. That consists of Emergency Coordinator Ann Lesage at City Hall, Deputy Chief Jared Moravec from the Fire Department, everybody's favorite Executive Director, Lauren Bast, and myself. That's at 1 p.m. sharp. So Ann's running our overall digital show this morning, so you might likely see her pop in and out of here with announcements as well as when we're handing it off from speaker to speaker. So we are super excited to have three speakers with you today. Dr. Stephen Angster, Dr. Jessie Pearl. They're going to present the history of earthquakes here on Bainbridge Island, which will be very cool. And then Dr. Avanti Bergquist will speak on emotional resilience at 11:30. So a bit of background for you on our first two keynotes before I turn the microphone over to them. Dr. Pearl, I'm going to read this to you because I did not memorize their bios. Dr. Pearl is a Mendenhall Postdoctoral Research Fellow with the U.S. Geological Survey. She received her PhD in geosciences from the University of Arizona. She uses multiple techniques, including, Doctor, you can laugh at me for this later, Dendrochronology, which is the study of tree rings, and I'm sure I just mispronounced that, and geology to describe and analyze past landscapes, extreme events, and climate. Her current project uses trees killed in earthquake events to precisely date the land movement and characterize the spatial extent of forest damage. This enables her to build records of past landscapes that can inform our understanding of current global change, as well as future hazards. Our second keynote this morning on that's presenting with Dr. Pearl is Dr. Angster, paleoseismologist with the U.S. Geological Survey, who specializes in finding and characterizing active faults in the Pacific Northwest region. The goal of his research is to understand where, how often, and when the last large earthquake event occurred in the high-risk areas like Puget Sound here, both east and west of the Cascade Mountains. Dr. Angster is originally from the Midwest. He's got a master's degree from the Colorado School of Mines, PhD from the University of Nevada in Reno, and he's been with the USGS for about 10 years, and he studied faults all over the world, including the Himalayan frontal thrust, known as the granddaddy of them all. So with that, please welcome Dr. Pearl and Dr. Angster to our webinar with me. I will turn over control to them.
Hi there. Thank you. Let me get my screen set up. Thank you for the intro. Yeah, I forgot I put in granddaddy of them all there. So yeah, Himalayan thrust is a big one. But thank you for inviting us to share some research with you all about what we've been doing and our continued research of the Seattle fault, which is what we're going to kind of focus on today. Let me get my screen set up here. So today we're going to be talking about some ongoing research that we and some others here at our little USGS office here in Seattle are doing on Bainbridge Island to better understand the hazard posed by the Seattle fault. As many of you may know, Bainbridge Island is kind of this portal, I think, into the Seattle fault. There's been many studies done on the island, and these are ongoing, and we're kind of continuing these with new methods and data that's been coming out. So our goal today is really to provide some insight into what we know and don't know about the Seattle fault in relation to seismic hazard to help with your day of preparedness. And as I'll show you in the next suite of slides, and Jessie will continue on, is that the Seattle fault is quite unique compared to, say, faults in California. And it really forces us to come up with these new creative ways to understand its behavior and kind of the magnitude of it all. And so all of our work really goes into this National Seismic Hazard Map, which is down in the lower right part of your screen, which helps guide insurance policies or building codes and everything. So it has a big impact, really, and there's lots of people who study on focused regions as well and kind of focus hazard maps within a region, say, like the Pacific Northwest. So Jessie and I are part of a group that's based out of Seattle that researches and monitors seismic activity within the Pacific Northwest. And as many of you know, seismic hazard is driven largely in the Pacific Northwest by the interaction and differential motion between the North America plate and the Juan-de-Fuca plate, and the boundary of which kind of lies offshore and forms a subduction zone. And subduction zones are really the most hazardous types of plate boundaries because not only are they capable of producing the largest earthquakes, they're very dynamic in that they have volcanism associated with it, and they have a big influence on how this upper plate or North America plate deforms. And so there's really three types of hazardous earthquakes that kind of result out of this plate boundary. Is we have the subduction zone event, which is the big one, which could produce up to or over potentially a magnitude 9. We have these deep intraplate events which occur in this Benioff zone. And the 2001 Nisqually earthquake was one of these. I forget the actual magnitude of that. I think it was around a 7, but these are very deep earthquakes that are within the subducting oceanic slab. And then we have shallow upper plate earthquakes, which originate within the North America plate, which overrides the subduction plate. And that's what the Seattle fault really is representative of, is one of these shallow upper plate faults. And so a lot of the faulting in the upper plate occurs in response to the slow ongoing clockwise rotation that we have in the Pacific Northwest. And this is really driven from the oblique motion that the subduction zone has And the big map on the left here shows the velocities of permanent GPS stations. This is data collected over 10 years. And this is showing the relative motion of kind of the Western US as a result of the interaction of these plate boundaries. And as you could see, the longer arrows obviously represent faster velocities, but as we move to the east, these velocities decrease, but they extend all the way until, say, Salt Lake City. But in the Pacific Northwest, we have this kind of slow clockwise rotation going. And geodesists, the people who study these velocities, are able to measure the amount of deformation that occurs. And so in the Pacific Northwest, we have about 5 millimeters a year of north-south oriented contraction that's ongoing. And this is west of the Cascades. To the east, it's about 2 millimeters a year. So the big question that's kind of laid upon me in my job is, where is this deformation being accommodated? And so we have a pretty good idea of where the active faults are within the Pacific Northwest. This underlying map here shows all the faults that we know of that are active and probably taking up most of this deformation. And as you could see in the Puget Sound region, there's kind of a cluster of them, and the Seattle Fault Zone being one of them. The SWIF is a Southern Whidbey Island Fault Zone. That's another large one that kind of cuts across to the northwest across the sound. And then we have the Darrington Devils Mountain Fault, and downway to the south, we have the Tacoma Fault Zone. So between these 4 fault zones, we expect somewhere between 5 millimeters a year of, we call it strain or deformation, to be accommodated. So if you split it up between the 4 of them, maybe a millimeter per year on each of them. But I'll get into why we call these fault zones. Why these faults are important is because they're very close to home. The maps on the right show our kind of shaking intensity maps of earthquake scenarios. The top one being of the big one, a big rupture on the Cascadia subduction zone. And as you can see, it affects a large area of the entire state of Washington, which in fact would continue all the way down into Northern California. So the big one would affect a very large area, but in Seattle and Puget Sound, we're really only in the orange area, whereas an event on the Seattle Fault or the Southern Whidbey Island Fault Zone, we would experience some pretty intense shaking within the Puget Sound region. So there's some big motivation to understand the behavior of these faults that are pretty close to home. But we have some challenges in understanding these faults. The main one, let me back up one, is that we have a relatively slow deformation rate. 5 millimeters a year isn't really fast. To put in perspective, the San Andreas accommodates about 50 millimeters per year. That's about as fast as your fingernail grows. So 5 millimeters a year is pretty small compared to that. So our reoccurrence rate, or the frequency at which the earthquakes occur, is relatively slow, or a long period in between. Second challenge we really have is, since we have this long reoccurrence interval in between earthquakes, we have kind of compounded on that as we had these glaciers come through and really reset the landscape within the Puget Sound. The land surface was essentially scraped clean during the last glaciation about 16,000 years ago, and it really wiped out any evidence of prior earthquakes on these faults that occurred before then. So In essence, this is good for finding active faults because any fault that ruptures a surface, we know is active because we know that the landscape is reset to about 16,000 years. So that would deem it as active, but it's bad for extracting these long-term earthquake histories, which we like to know for reoccurrence intervals for seismic hazard analysis. So the glaciers created this beautiful, what we call fluted landscape. And these maps on the right kind of show some detail, these north-south striations that remain on the landscape. And those will come into play as we kind of focus on our study here. One other thing that occurred after these glaciers started to recede is that we had these series of lakes, and they have all these different names, but they kind of culminate into what we call lake breadths. Until the glacier kind of receded to the Juan de Fuca Strait, and then it was introduced to the ocean, it was all freshwater until then. And this will come into play later as we get into the trench we dug this last summer. All right, and the third challenge we have, which kind of brings me to the Seattle fault, is many of these faults in the Puget Sound are kind of invisible at the surface. What we know about the scale, the size, and the length of the Seattle fault mostly comes from geophysical studies that kind of use the physical properties of Earth, say the magnetic density, gravity field, to make these interpretations. And so this kind of psychedelic map that you see at the bottom of the screen is an aeromagnetic map. And this shows the fluctuations in Earth's magnetic field along the Seattle fault zone. And these linear features that are marked A, B, and C kind of denote where the Seattle fault is. And we can see this kind of sharp change in the gradient where we're going from these blue colors, which represent kind of low or maybe some polarity of the magnetic field, to green. There's a big sharp change occurring across the Seattle fault. And these east-west lineaments that occur kind of are marking where the Seattle fault is within the subsurface. The map above shows these lines as white lines, or shows these lineaments as the white lines. The red lines in the map are showing where we have actual fault scarps. These are where the fault actually broke the surface and ruptured the surface sometime after the glaciers were here. And as you can see, they're kind of discontinuous and don't extend along the entire length. So they provide these bits and pieces of information of this bigger feature. And so, and of course, many of these are on Bainbridge Island, to why Bainbridge Island is kind of special to us. So prior studies or other geophysical studies have shown why this fault is invisible, because it's really a blind thrust fault. So that's a fault that doesn't reach the surface as kind of one main strand. It kind of spreads out into many other strands and kind of complicates things and makes it difficult for us to understand a full rupture history of the fault. So one of the big questions that we have are, what are these smaller faults representative of? Do they rupture every time that there's a big earthquake on the main Seattle fault below, or do they rupture independently? Do these smaller faults above and within the shallower subsurface, are they capable of generating earthquakes? So these are some of the questions that we're trying to answer currently. The toe jam scarp, which you may be familiar with, which I've kind of pointed on the screen here, is one of these back thrust. So it's kind of a north dipping thrust that parallels geologic bedding planes, but it's really the smaller fault that kind of splays off of the main strand. And so this makes it pretty difficult to characterize really the seismic hazard for the whole Seattle fault. The best evidence we have for a large event on the Seattle fault is this elevated marine terrace in Puget Sound that only exists within the Seattle fault zone. And that's shown by the red lines on the map below. Restoration Point and Elki Point are really the manifestation of this uplifted marine terrace. And this represents a major uplift event that occurred, we think, 900 to 930 years ago, probably a result of a magnitude 7+ earthquake. And Jessie's gonna kind of wow us and the power of her research of how she could pinpoint the date of when this occurred. But this was a major event that uplifted the land and probably generated a tsunami, or it did generate a tsunami in Puget Sound. We find evidence of this from tsunami sands at Discovery Park, but it also probably generated a tsunami in Lake Washington and possibly Lake Sammamish. So the black lines on this map are these smaller fault scarps that we're going to start to focus in on now and get into what are they representative of the Seattle fault. And as you can see, most of them are on Bainbridge Island. And many of you might be familiar with some of these. We have the Islandwood Scarp up to the north, kind of a short little feature. The Toe Jam Hill Fault Scarp, which has been studied quite a bit. And these scarps, and then the Waterman Point Scarp over to the west. And these scarps are really discovered when LiDAR data was acquired over Bainbridge. And LiDAR data allows us to generate these kind of bare earth images of the surface without trees. And so fault scarps really show up as these really distinct, sharp lineaments that cut across this fluted glacial landscape. And as I was about to say, the Toe Jam Hill Scarp has been pretty extensively studied. There's been several paleoseismic trenches dug across it. And what we know is that there have been up to about 4 earthquakes that have occurred on this fault since that major uplift event around 900 AD. So it appears that these smaller scarps are rupture independently of the main fault underneath. And so yes, they can produce their own earthquakes, probably much smaller than the bigger Seattle fault can, but these are even more closer to home for you guys, so something to be aware about. Now to focus in on our most recent study, we found what we're calling the Blakely Harbor Scarps from a new LiDAR data set that came out in 2018, which was higher resolution data. And we're going to zoom in on this region here. So this upper map kind of shows a blank elevation model, and the lower map here is the interpretation of this. And so we have these east-west linear features within the landscape that to us look like fault scarps. And so the big question we have is, are these actual fault scarps? The other alternative is that they could be bedding planes or geologic contacts. So, and if these are fault scarps, we want to know when did they last rupture and how big? And so there are several features that we also observe along these scarps and that we're continually doing research on. On the left or to the west, we have our 900 AD terrace, which was that big Seattle uplift event. And then inset to that and a little bit lower, we have this younger terrace, which is, well, I'm blanking at the beach right now. But this younger inset terrace, which we really don't see anywhere else. And so it's pretty localized to this area, and it appears to be right on trend with our potential fault. And then over to the east, near where Blakely Harbor is, there's the mill pond, which Jessie is going to talk about that. But there we have these old dead trees that we suspect were drowned by an event on this fault. And so really, to get at the question on whether or not this was a fault, we dug a trench across kind of what appears to be the main scarp of this feature this last August. And because of COVID, or the pandemic, we really weren't allowed to hire an excavator. So we dug it by hand, which was quite a task. And we have to thank Mark and Jenny Donahue, the landowners here, for allowing us to really just dig the biggest hole that I've ever dug on their property. But we're able to dig the entire trench within a week, and kind of jump into what we observed in this trench. Up top is a photo mosaic of one of the walls of the trench. And basically what we found was a sequence of alluvial, lacustrine or lake deposits and glacial deposits that's all overlie bedrock. And that we found that these glacial and lacustrine deposits were actually folded and faulted at the lower right. And the interpretation below, or this is really the log, the red streak running across is where we mapped the small little fault that displaced these glacial and lake deposits. And so we're interpreting a larger kind of underlying fault to explain the geometries that we observed in this trench, to explain the folding that we see, and it probably connects to the smaller fault that we observed in this trench. And so we're pretty sure we have a active fault here. And we collected a bunch of charcoal that's currently in the mill and for age dating, and it's going to give us some constraint, hopefully, on the timing of these earthquakes. One more thing, just to add a little bit more detail. Another key thing that we found within the trench are these buried soils. We have two of them that are buried, and then a modern soil above. So we actually think we are seeing multiple events here. So definitely 2, possibly 3 earthquakes. But this is ongoing work, and our pending age results on these charcoal samples is going to tell us or constrain us to say how many events we have. But that data should be coming in the next couple months, and we'll be working on that through the next year. So the fault that we observed in the trench really could explain this younger terrace, which should post-date the 900 AD main uplift event. And we have future plans to constrain the age of uplift or formation of this younger terrace and see if we could correlate that age to the trench. And then Jessie, who's going to talk in just a moment, is going to hopefully find an age of when this mill pond formed. And I'm going to hand it over to her so she could inform you about that.
Awesome. Thanks so much, Steve. Yeah. All right, I'm going to now share my own screen. All right, hopefully you can all see my slides now. Yes?
Yep.
Great. Thank you very much for having us. Once again, I'm just going to reiterate what Steve said. We're really excited to share some of this ongoing research with you. We're really jazzed about what we found, especially since so many of these features have been overlooked for so long, and it's kind of discovering in a whole new way some of the fault mechanics and some of the hazards we have on Bainbridge Island. Yes, dendrochronology, you pronounced it absolutely perfect. A little etymology, dendro as in dendritic, trees, branches, you have dendritic nerve endings. And then chronology is through time. So trees through time, it's the study of using tree rings to tell us something important about different processes over the past few thousand years. And specifically, I'm going to talk about how I'm using dendrochronology to get high resolution dates. And when I say high resolution, I mean the uncertainty is down to the year, maybe even to the season of these larger earthquake events in the Seattle fault zone area. So my big component of this, well, how can we improve upon these ages? Radiocarbon dates that we're pulling from these trenches are really wonderful to help us constrain and give us bookends of when things happened. But unfortunately, they have uncertainties from anywhere from 50 to 200 years. So we want to get better ages because of a few reasons. One, it's better for us and our models for recurrence probabilities, but also it's really important to be able to detangle separate events. Within radiocarbon uncertainty, sometimes certain earthquake events can look like the same event, and it's really important to know if those earthquakes are indeed clustering or if they are separate events that actually aren't interplaying with each other. So really getting back to the actual mechanics of how faults are interacting in this region. So Steve already showed you this LiDAR image of our Blakely Harbor fault scarp zone. Just once again to orient you, we've got the trench over here on the western end of this image. And then we have the mill dam pond, which I've circled in red. That our hypothesis is that this wetland, this pond, was actually dammed by the rise of the fault scarp. So whatever creek or stream was draining this low-lying area was blocked off by the formation of the fault scarp. The water then backed up that low-lying area and drowned all the vegetation that was in that area. So we're looking to find a suite of evidence for this most recent earthquake that might have actually dammed up this pond. Now, our very first sort of question that might give us pause is to think about, well, what is the history of the island? So in the mid-1800s, I'm sure everyone on this call knows the Port Blakely Mill Company had an absolutely massive presence, not only in terms of the infrastructure that was built, but also in terms of the vegetation. So most of the trees on the island were indeed cut down. A lot of the waterways might have been manipulated by humans. And it's a little suspect as well because we're calling this mill dam. So the idea that humans might have actually dug or dammed this pond itself and it's not a fault scarp dammed pond is a real possibility. We can even see on the LiDAR imagery where there is a very clear human dug trench between these two mill dam ponds. So we need to make sure we have a really comprehensive suite of evidence to say that this is indeed a fault scarp dammed wetland and pond, and it's not just human dug for water for the mill for putting out fires, for example. And if you've ever walked or rode your bike or walked your dog along the Blakely Cemetery Trail, Blakely Harbor Cemetery Trail, you might have actually seen this little pond. It is, I swear that's water. It is almost always covered in vegetation, duckweed or little algae. So the actual water itself looks green pretty much throughout the entire year. We visited in all of the seasons so far. And they have these really charismatic standing snags of red cedar. So Thuya plicata, so Western red cedar. And Western red cedar is an incredibly hardy species of tree. That's why many people have used it for shingles, boats, and furniture. It tends to be extremely rot resistant, which makes sense why it would persist in the landscape, specifically in this landscape where it's so wet. And one of the reasons we think that this might be an area where these trees were killed by the damming of this pond is because this does not look at first glance like these trees were cut down and then killed later. In fact, you can see how these snags are sort of sticking up. They don't have that nice flat surface of where someone might have sawed the tree off, or even to have those notches that are kind of characteristic of first growth, old growth being cut down. So here's the big question. Did an earthquake, and when I mean earthquake, I'm thinking specifically about the land movement, the fault scarp that's formed because of the earthquake that dams that water. Did this earthquake kill this ghost forest? So I call these trees that are standing in the landscape and clearly have been dead for hundreds or even thousands of years, ghost forests. That's just an image that kind of comes to mind of these ancient landscapes that clearly could not actually live in the modern day scenario. So these trees, no trees grow in this mill dam pond now because it's too wet, it's probably too anoxic. However, we see evidence of the past landscape that used to be here, that clearly something very dramatic had to happen to have this particular landscape change so quickly and have these trees persist without having gone through the full decomposition process. So if you have lived in the Pacific Northwest and you're aware of Cascadia subduction zone earthquakes, you've most likely heard this term before. Ghost forests along the coast of Washington are very famous. And they're famous because many of these ghost forests, specifically Western red cedar ghost forests, helped date the 1700 subduction zone earthquake. This is an example. This is me out in a ghost forest along the Bone River. These cedars are clearly much taller than the ones we're finding on Bainbridge Island, but you can still see some snags in the environment that do kind of calibrate our eyes to what a standing snag of red cedar might look like in a ghost forest. And these trees died all at the same time, very rapidly at the year 1700, because the land actually dropped and subsided enough that the ocean water and the salt water encroached into the area and killed the trees. Trees can't, especially cedar, can't grow in saline water. So all of these trees died. And we were able to use dendrochronology, so tree ring dating, to get that precise death date and then give us a sense of when this large subduction zone earthquake happened. So why focus on trees? Why do we really try and pick out tree rings as a part of evidence for paleoseismology? Well, trees are absolutely incredible storytellers. They stay in one place their entire lives, and each and every year they put on an annual growth ring. And that annual growth ring, if you've ever looked at a cross section of a tree before, you've seen that light wood and that darker colored late wood that represents 1 year. And within the physical and chemical characteristics of these tree rings, we can derive relationships with climate, with ecology, with fire. And ultimately, if the tree died in a really traumatic event, like a landslide, a big tsunami, or an earthquake that might have drowned the tree due to the formation of a fault scarp dammed lake or a sag pond, we can then date that traumatic event. So how does this work? Well, myself as a dendrochronologist goes through the process of what we call cross-dating. So trees thrum in time to climate. And what do I mean by that? Trees are going to grow well, so they're going to put on a larger annual growth ring when the climate of the area is good. So when there's enough light, there is warmer temperatures, there's enough rain, it will grow well that year. If it's dry, there's a drought, possibly it's a very cold year, maybe there's an ice storm or a frost, that tree will grow less. And that pattern, that barcode of big rings, small rings, is very unique to the climate regime of the area. So it's very unique to the particular region we're looking at. And if you can find a living tree and take a barcode of that living tree, and maybe the youngest years of that tree overlap with a historic log cabin nearby that has older wood, and that can extend that tree ring chronology even further back, and maybe those tree rings overlap with standing snags in the environment, and that can push that chronology even further back. And then maybe you can even find trees that are buried in the environment and have up to 8,000 year long chronologies is the longest we've had. So trees can give us a record of climate or of events for over 8,000 years. Now, unfortunately, here in Seattle area, we don't have these multi-millennial length chronologies. The farthest we go back is about 500 years or so. So we're really dependent on our ability to cross-date the wood with themselves to really lock in that timing and hopefully get a much better date. So what do I mean by that? Well, if I kind of zoom out from the Bainbridge Island area and we go into the whole Puget Lowlands, and this is a LiDAR image where we've highlighted in red the different fault zones. So the Seattle fault zone, the Tacoma fault zone. In the purple triangles, this is evidence for coseismic uplift, so fault scarps, the one that Steve just mentioned that we dug a trench through. In green triangles, coseismic subsidence, so where the land actually went down because of an earthquake. Usually this is representative of buried soils. And then we also have labeled all of the ghost forests of the region that I have worked with over the past year. And so what we see is that in many of these earthquake zones, and particularly in areas of coseismic subsidence, we have these ghost forests that are preserved in the landscape. And a few of these, or quite a few of these sites are actually, we've done the cross-dating method to determine that all of these trees died in the exact same year. So some of these are fault dammed lakes like the one on Bainbridge Island where the trees are just drowned because of the back infilling of water. Some of them are large block landslides like Lake Sammamish. The entire side of the hill went down into the mountain, or went down to the lake, excuse me, because of this earthquake. You can still see the trees sticking up if you've ever been to Lake Sammamish. And then Lake Washington as well, large, massive earthquake events, and then tsunamis. And by determining, because those barcodes match so well that they all died at the same time, we then needed to say, well, how do we get this age even better? We know that it's around 900. That's what radiocarbon tells us. Can we use trees to do one better and get the exact year? And that's where we turn to the tree ring chemistry. So what I'm showing here is a graph of radiocarbon. Specifically, we're looking at the year 774, 775, where this known jump in atmospheric radiocarbon, and this is seen throughout the entire world, this jump. And by finding the jump within the Lake Washington and the Hamma trees that we've collected, we then place that tree ring ghost forest chronology exactly in time. So we're able to use, we can think of this almost like an ash layer from a volcano event. These big spikes in chemistry to lock in those chronologies exactly in time and tell us that that last big Seattle fault zone earthquake happened in the winter of 923, 924. So after the trees went dormant for the winter, they put on their late wood, and then before the trees started growing again in the early spring of 924. So this is the power of dendrochronology, right? We can actually get these dates down to the actual year and then say something powerful, not only about the spatial extent, how widely that Seattle fault zone earthquake was felt, but also the other ghost forests that weren't involved. And that's actually a different event, a separate event. So it's a really powerful tool to be able to look at past earthquakes. Now, this is our argument. Do we possibly in the Bainbridge Island have another ghost forest? Well, there's a lot of questions we have to answer before we can say for sure that this is a paleoseismic site. And the very first one that I alluded to is, well, was this wetland formed by humans? Was this a wetland or a pond that was dug in the mid 1800s to early 1900s for a water source for the mill? When did this wetland form? And then the second question is, well, did these trees die by drowning in this wetland? Did the trees actually die because of some traumatic event, or is it just a natural cause? And the way we can answer that is figuring out if the trees all lived at the same time. If we find trees that lived at different times, it's more representative of a natural forest system where trees are dying at different rates. And then the last part of this is, well, can we use the trees to better determine and nail down that death date at a more precise way than we can with just trench radiocarbon, so bulk radiocarbon. So we went out and we took a gouge core. My supervisor, Brian Sherrod, is modeling very nicely our gouge coring technique. We went out to the pond and the wetlands surrounding, and we took a transect of cores. You can see the snags. If you look through the reeds there, you can see the snags of the red cedar of this pond. And we got about a meter, almost a meter of wetland peat and mud before we hit that glacial blue-gray clay, excuse me. And if we think about sedimentation rates in the area, we assume that we have about 1 to 5 millimeters of sediment accumulation per year in a wetland environment. That's pretty typical for this area. So if we just do a back of the envelope calculation, just based upon the amount of sediment we were able to extract from this core alone, it looks like we have at least a 300-year-old wetland, and maybe even as old as an 800-year-old wetland. But to do one better than just back of the envelope, we also pulled radiocarbon from this core, and we tried to get radiocarbon as close to that transition between glacial material and wetland material as we could. So we were able to pull charcoal, which is representative of kind of the oldest possible date. The trees that were on the landscape that would have burned most likely would have been old growth and very old. So the 1300s is probably the oldest date this wetland is, and then seeds, which kind of represents that upper bound, where the seeds that are incorporated into the wetland peat and mud could actually be younger than the wetland itself. And that's bounded at mid-1600s to 1800s. So what does this tell us? Well, this tells us that the wetland most likely predated the European settlement in the mid-1800s. And the wetland further most likely formed between 600 and 300 years ago. So that's kind of one check off of our list. We are pretty confident that this wasn't a wetland that formed just when the Port Blakely Mill Company was around. So the next step is to try and go out and take some of these tree samples to answer those remaining questions. So I had to put this picture in here because we are trying to make stand-up paddleboard dendrochronology a thing. I've never done it before personally, but we used a blow-up kayak and a stand-up paddleboard to get to these trees. It might not look it, but the standing water here is up to 4, even some places we think 5 feet deep. And so we needed some sort of flotation device to get out there and appropriately sample these trees. In some cases, we were able to take hand saws and saw off pieces of the trees. And in other cases, I used an increment borer. You see me using that on the right-hand side, which takes out just a pencil-sized core. And I'm just gonna give a little spiel about increment borers so that you're not afraid of dendrochronologists in the future. We really don't want to have to cut down every tree we want to sample. That would make us very bad scientists and no one would let us do our work. So we use an increment borer. These are very sharp tools that bore into the tree, and many of you know this, but the living part of the tree is just on the outside underneath the cambium, underneath the bark, and we take a pencil-sized core out. And this pencil-sized core actually has all of the information we would need, just as good as a full cross-section or a wedge of a tree. So this allows us to take samples from larger trees, especially that we can't get good hand saw samples from. And we were really, I personally was really surprised at the quality of samples we were able to get, especially looking at the trees. They look very eaten out by vegetation, animals, they look slightly decrepit, but we were able to get samples from 12 trees that are really beautifully preserved wood. So what you're looking at on the top 2 pictures are some of the nicest looking sections we got with the handsaw. And I just want to reiterate, I'm actually holding one of them here. These are not big samples. In just this small sample alone, we have over 200 years of growth. So there's quite a bit of growth happening in these trees, just in the little the outermost rings at the end of its life. And we also were able to get just really wonderful cores of some of those larger trees that go back, in some cases, 300 years. So to calibrate your eyes, so what I'm seeing as a dendrochronologist, I'm putting up on this slide a modern Western red cedar tree core that I took from this same wetland. It's just a living tree. And then on the bottom, the ghost forest western red cedar. And you can see that the year right underneath the bark on the left-hand side is the year 2020. And about halfway to 2/3 of the way down the slide, you have the year 1990, so 30 years later. And in that same amount of space, and if we're just thinking qualitatively, we have 100 years of the ghost forest western red cedar. So what does this say to me? Well, this says to me that this is not second growth. These trees that were sampled are old growth trees, and this is just further evidence that this is not an area that was cut down and then allowed to flood later. These are trees that were standing in the landscape for quite a long time and very much representative of old growth trees rather than second growth or third growth. So we take these samples and under a microscope or with a very high precision scanner, we are measuring the ring widths. And this is our first step in being able to cross-date the trees. And what I'm showing here is the measurements of all the different samples we took in black, and then the mean is in red. And what we find is that the trees are thumping along to that same climate drum. They agree in their ring width pattern extraordinarily well, better than even modern trees that we know the actual ages of. And this gives us information and evidence that these trees likely died at the same time. And moreover than that, they likely died at the same time. So you can even see just in the raw measurements, it looks like spaghetti plot in some ways, but you can see these big dips and growth that all of the trees are doing in synchrony. And so this is really good evidence and very strong evidence that these trees are a contemporary cohort. So if I try to slide, oh my, I am frozen. Uh-oh. There we go. So if I do an initial cross-dating with other long western red cedar in the area, we get a suggested date of mid to late 1600s of a death date. I don't put too much stock in this, however. Unfortunately, the other long 1,000-year length western red cedar chronologies that exist in the western United States are over 120 kilometers away each. And for me, I know that the climate regime of Vancouver Island and the climate regime of southern coastal Washington is different enough from what we're seeing on Bainbridge Island to know that there could be just spontaneous or not correct agreements between the tree ring patterns. So we want to be better than that. We want to actually make our own master chronology for the area, and we are working on that. But before we can get that, we can take the radiocarbon just to give us a sense if things are starting to line up. And indeed, the initial radiocarbon we got from outer rings of 2 of the samples date to 1500s to the mid 1600s. So far, all of these radiocarbon are kind of aligning, the formation of the wetland with the death of the trees, and then also on top of that, with that cross-dating with other chronologies somewhat nearby. And as Steve mentioned, this is ongoing work, and a lot of the radiocarbon has been backed up. The lab's slightly overwhelmed as things started opening up, but we have more radiocarbon dates coming soon, and we're really excited to really nail this down even further. And better dates are also going to answer this question, well, maybe we're not just seeing one event, maybe we're seeing multiple events here, and that makes this particular site an even more engaging and interesting story for me as a paleo landscape geologist and a dendrochronologist. Maybe we're looking at the impacts of a 13th century fire. We do see some burning on the wood. That would explain the charcoal age that we got. And then later, the wetland formation that might have killed any other secondary growth after those old growth trees experienced the fire. So what does this all mean? Well, we have a few things that we can say for certain. The Mill Dam Pond wetland, it definitely predates the Port Blakely Mills as far as we can tell. The wetland is probably 600 to 300 years old. The pond itself, looking at the LiDAR imagery and also thinking about how this wetland might have formed, is likely dammed by the fault scarp. And we can see that both in the LiDAR imagery and as well as having seen that human dug trench that drained that pond into the lower lying wetland across the road. The ghost forest that exists in this pond, we have about 12 trees, so a smaller forest, if you will, has old growth trees preserved. Many, if not all of these trees lived at the same time and perished in the 15 to 1600s. The more radiocarbon we get, the more precise radiocarbon, as well as that regional red cedar chronology, that's going to nail that date down to, if not the decade, maybe even the year. And this is all going to happen within the next year. This is going to greatly improve our interpretation of this site. So at this location, along the Port Blakely area, we have a convergence of evidence, dendrochronological, stratigraphical, chemical, in the terms of radiocarbon, that's all coming together to build this story of this most recent earthquake event that is completely separate from that large 923 event. So it's a splay fault event, a smaller localized event that has implications for Bainbridge Island itself. And just to kind of placate in the sense that we're not toting doom and gloom, we're not super excited about earthquakes coming to Bainbridge Island, we're just really interested in actually uncovering all this evidence to build this more, this better and more accurate model of earthquake hazards in the region. A full rupture along the Seattle faults would likely produce a large magnitude earthquake, 7 or higher. Most likely would also generate a tsunami that is localized, but the chances of that happening within the next 100 years are low. Considering that the most recent large Seattle fault zone earthquake was 923, the strain rates are low. This all gives us pause to think that the next one won't happen for some time. But we are more likely, and we see that in examples of that smaller fault scarp that Steve talked about, this Mill Dam Pond that's dating to that 1500, 1600 age range. The Bainbridge Island community is more likely to experience smaller earthquakes along these splay faults off of the main Seattle fault. And these are the types of faults we really want to characterize better to have a good understanding of earthquake preparedness. So those are the slides I have. I would like to once again promote stand-up paddleboard dendrochronology. But Steve and I are going to leave it off on this slide. There are lots of resources out there for you if you're concerned about earthquakes and hazards, how we interpret all of this data and what is available to you as resources for preparedness, and then just information for your own understanding of how earthquakes are thought to have worked in this area. Thank you.
Thank you very much. That was wonderful. So we've got some questions. So Docs, if I can ask you to click on that Q&A tab that you see down there. And you've got both kind notes from Dawn and from Lisa, and then you've got a couple of questions in there as well if you want to pop back in there and start up maybe up at the top with Fred's question.
I'm going to punt that to Dr. Angster.
Okay. Doctors, how much in millimeters per year of release or movement would be required to produce the magnitude 9 event? Well, in a subduction zone earthquake, say like the big ones that occurred in Tohoku and Sumatra, these are big events or slip events that occur underwater. And the amount of slip that's occurs during that event is pretty large. So large enough to generate large tsunamis in the ocean that travel across the Pacific. And so in a large magnitude 9, there's probably up to, I'd say, 7-10 meters of slip that occurs at the surface of the ocean. And so it's that displacement that's released that produces a tsunami. And so when we back that out to millimeters per year, so a release of, let's just say 5 meters of that let's say we have 5 millimeters a year, which we have in the Puget Sound region. we have 5 millimeters a year. And so on a fault, say like the Seattle fault, which would probably displace the land maybe up to a meter or two, that's kind of like a 10,000 year, 9,000 year recurrence rate, we think. Does that answer your question? I hope.
They might be muted.
Okay, well, I hope that does.
I'll take the next one. What does CE mean? I did realize that when I saw Steve's presentation, we're using different labels for our years. So in Common Era is what CE stands for, as opposed to BCE, before Common Era. So in the AD, it's AD, but it's as opposed to a religious connotation, it has a Common Era connotation, past 2,000 years or so. Mm-hmm. And then let's see, I didn't understand. Yeah, okay, so so the growth conditions of the trees themselves, assuming that the trees were not in a pond when they were growing, and that's something that could always be possible, but it is our understanding that trees with their roots underwater in this very anoxic environment would have a very hard time growing. And that's one of the reasons why we don't see any modern trees growing up in that pond. And so our assumption is that the trees, when they were growing, were in an environment that was conducive to their growth. The tree that I showed on the top, that's actually the red cedar tree that I could find that was closest to the standing body of water. So in my mind, as close as I could get to as potentially an analog tree for what that the old growth trees were showing. There's a few things at play here. The tree that is modern is maybe 100 years old or so. And if you think about a tree that is growing in circumference, each and every year, it has to put on more matter, more mass, excuse me, to fully envelop the larger circumference. So we call this a geometric growth trend. The rings of a tree are going to get smaller naturally the further you get towards the bark. And that's just because it's a matter of geometry. The bigger the tree gets, the more mass the tree actually has to grow around the entire circumference. So thinking about that, we would expect a larger tree, an older tree, to just have smaller rings. On top of that, the second growth trees are also having much less competition for resources than that old growth tree had. So in a forest, in an old growth forest, you have stand dynamics, you have shade blocking the canopy. Those trees are going to have to fight for resources like light, like water. In a second growth forest or a third growth forest, assuming you've cut everything down, those younger trees are going to have no problem at all growing super fast, super tall, super big, putting on large rings, because they're not competing for those types of resources. So there is always the possibility that, yes, back in the 1600s, these trees just were growing in really poor conditions towards the end of their life. My argument would be it's unlikely that the tree would face over 200 years of poor conditions, and that alone is the cause for the smaller rings. I think it's just a more simple age of the tree is what we're seeing in the actual size of the rings themselves. But that's also why we turn tree ring widths into indices, so we're not fooled by just associating size themselves with patterns. We do detrend for the growth, and I do a couple different statistical processes to make sure I'm not being tricked by the actual size of the ring itself.
I'll take the next one, ETA Studio. What instrumentation is there on BI faults? Strain gauge, question mark. We don't have, I don't think there's any specific instrumentation laid out across these faults to measure deformation. Say like a strain gauge. I think the closest thing we would have are kind of an array of GPS stations around Puget Sound, but they're relatively sparse compared to the density of the fault network per se. And the problem with GPS in trying to determine where strain is accumulating is that these faults are rupturing on multiple 1,000-year intervals. And so the GPS has really only recorded, say, the past 10 years. So, and we only get that signal when they rupture. The intermittent time between earthquakes, there isn't much of a signal. So it's kind of difficult to parse that out and where this strain or deformation is focused on. Terry, what magnitude quakes are likely to result from these localized island faults? So that's a big question. The expression of these faults is really limited to the kind of the width of Bainbridge Island itself. We see that the toe jam fault, if we follow it further to the west, doesn't really show up on Waterman Point. So we think it's a relatively short fault, which would limit the magnitude potential of it. But the fact that it does rupture the surface tells us that it probably could produce maybe a magnitude 5 earthquake, which would be quite alarming for Bainbridge.
That kind of also gets at the second question too there.
Okay, yep.
I think it's a great suggestion to consult with local tribes, especially with the more recent earthquake event. And that's something that I have considered, but haven't actually pursued yet. And these results that are actually quite new in terms of the ages that we've been getting. So I think that's a really wonderful next step that I am looking to take. And we've been doing that with other earthquakes across the Puget Lowlands to talk with the tribes.
Yeah, I totally agree with that. And kind of our most famous geologist, Brian Atwater, does a lot of outreach and looks at these records. He's the one who actually found the buried tree at Discovery Park. It's a buried tree that was buried by tsunami sands during the last 923 AD event. But I'm not sure of any historical record that it would match to, but yes, something we will look into. How large, where are we at?
How large were the tsunamis that have occurred?
Oh, right. So if you go to Discovery Park, out on Magnolia Point there, the tsunami that occurred within the sound covered that surface of where that lighthouse is. And I think it's about 3, maybe probably 6 feet above the high tide line. So it's a pretty decent sized tsunami. Probably a tsunami, a larger tsunami than what a subduction zone tsunami would cause, just because it's so localized and it'd just be so immediate. It'd also be very quick right after the earthquake occurred. So whereas a big subduction zone tsunami would take about 12 minutes to reach land, this one would be generated pretty much immediately after the earthquake ruptures. So pretty hazardous event.
Answering Michael's question, yes, the dates are coming in as fast as we can nudge them along. And we are in contact with people on Bainbridge Island to get those dates out, and hopefully to you as well, once we have a better, at least from my end, sense of the mill dam ponds specifically, as well as the frequency that Steve's finding in his trench.
I'll take Phil's question about why does this keep moving? Phil, using the modified Mercalli index, so that shaking intensity, and seeing if we could use the mill pond to kind of translate this into a measuring tool to calibrate how much shaking we could expect to endure. So part of our group, we work with a lot other research scientists who study ground motions within the Puget Sound region, and they're modeling, they're using basin geometry and other basin properties to come up with this 3D model to run earthquake scenarios through, to see how seismic waves travel within the Puget Sound region. I think from the mill pond, I don't think we'd be able to extract a lot of information from, other than I think the ultimate goal of our focused research here is to get an estimate magnitude of what size event these little scarps, relatively little scarps, could generate, which is probably, you know, around a magnitude 5 or 6. So an earthquake of that magnitude on those faults would be run through these simulations and give us a good idea of the shaking intensities that we could expect. But they'll probably be fairly high, given that they're so local.
I can take the next couple. So the mill pond is along, the trail itself is called the Blakely Cemetery Trail, but if you go to Blakely Harbor, and behind Blakely Harbor, there is a suite of trails, and there's actually a smaller parking lot that's just west behind Blakely Harbor itself. That's the trailhead where you can go, and it's maybe about a mile of a trail until you hit another road that goes up and over the fault scarp, actually, through some really beautiful forest, and the pond is there. So hopefully that answers that. And then interestingly, we haven't found any other ghost forests in the Puget Sound that died in the same event as the Mill Pond event. So we are definitely thinking that the event on Bainbridge Island is localized enough that it wouldn't have impacts that reverberate throughout the sound. That being said, you know, there's still quite a few ghost forests to go get into. Maybe we will find something that dates to the same age, but everything we've been working on right now is quite a bit older than the Mill Dam Pond event.
I think we semi-answered Joe Dietz's question about kind of the size of the smaller big one that it could occur on Bainbridge Island. But yeah, these are potentially magnitude 5 or 6 earthquake faults, and yeah, would impact Bainbridge pretty heavily, as well as Seattle too. The big uncertainty really is, again, the size of these faults, because the glaciers came through and kind of wiped out, and they carved the sound. So how far do they extend into the sound or into the water kind of remains unknown. There have been some marine surveys done that show, like, the Toe Jam Fault extends a little bit further to the east underneath the sound. And there's also a fault that shows up at Elkai Point. So whether or not the Toe Jam Fault extends all the way to Elkai is a big question, but it's hidden underneath the sound, where we have pretty relatively low resolution and different depositional events that kind of obscure our ability to see the faults. Ellen, if there was a big one on Bainbridge, would South Beach rise or drop? Did it rise following the last big one? Sorry I didn't clarify this. So in the big Seattle fault event, it's the southern side of the Seattle fault zone, or the southern side of the Seattle fault would go up. And so these, the Seattle fault is a south dipping fault, thrust fault, meaning it dips to the south, and the overriding block moves up and folds up. So yeah, south side would go up, north side, I don't know if it would go down, but it may go down a bit, which would increase tsunami hazard. And that's kind of an issue we have with the big subduction zone, is we have uplift and down warping during big events. What is the vertical displacement in the 1700 subduction zone fault earthquake? Jessie, do you know the magnitude?
Yeah, it depends. So unlike the Seattle fault zone that is very much localized to the Puget Lowlands region, this Cascadia subduction zone goes through all of Cascadia, so from Canada all the way to the north tip of California. So the vertical displacement, as one might assume, changes over that very large geographic area. But in Washington along the coast, we see meters of displacement, enough that entire forests are now in tidal range. So I would say 1 to 3 meters is a pretty, of subsidence is pretty standard out there. I'm not sure here, though, specifically what land movement was doing.
I don't think we'd have much influence of land elevation here from a big subduction zone earthquake, yeah. Rather than we'd feel pretty long period wave shaking. So it'd feel like you're on a boat during rough water, I think, for a pretty extended period of time.
So I'll take Lisa's question. This is my specialty in the sense of finding these trees that are somehow not yet rotted or disintegrated in the landscape. There's a couple of factors at play. One factor is the actual species of the tree. So a species like Sitka spruce, give it 50 years and it will completely disintegrate. It's not very hardy. It will decompose rather quickly. It doesn't really matter what kind of environment it's in. Whereas I mentioned cedar is extraordinarily hardy, and it's known for its properties of being able to withstand water wear. Unfortunately, it's not just species specific. It has most to do with the environment with which it's preserved. So a lot of these ghost forests that subsided into the landscape were actually very rapidly buried by mud, tidal mud flat along the coast. And this preserves the trees. So these ghost forests are actually buried in an anoxic environment. So the different buggies that would have come and eaten the trees can't, because there's no oxygen. And so what that means for me is most of my field work is slucking out in the mud and uncovering these buried trees out in the coastal environment. When it's a younger event, so 1700 event, this Bainbridge Island 1600 event, when the trees themselves are younger, you can see them persist in the landscape for longer just because they aren't as old. That's why you still see those standing snags that are 1700, but even just over the past 40 years, we've seen most of those very tall standing snags fall over, break off. So it's not uncommon within the past 400 years, I would say, to find dead and downed trees in the environment. But any further back than that, you really need an environment which has buried the trees and preserved them in some sort of anoxic casket that someone like me can go out crazy with a shovel and a chainsaw and go find and sample.
Barbara's question, if there's an earthquake on the Seattle fault, can you explain how proximity to the fault would impact us versus being on the Olympic Peninsula? Being in the Puget Sound region, it's a pretty severe impact being so close to the fault. Being that large population lives over the fault or on the fault, we could expect to have pretty intense shaking from a full event on the Seattle fault. in addition with a tsunami. So pretty severe impact as a result of the proximity. Being on the Olympic Peninsula, you would definitely feel it, but not as intense. The geology there's different. You're more on bedrock on the Olympic Peninsula, whereas in Seattle, to the north of the Seattle Fault, it's a basin which kind of behaves like jello during an earthquake. So more severe shaking in the Seattle Puget Sound area. Given another 1700 Cascadia event, how big would the tidal surge be on Bainbridge? And what would the delay be in arrival? I'm not sure in the exact times and the magnitude of a tsunami, but I will direct you to the Washington State Geological Survey. Go to their website. They have amazing videos and scenarios that'll show you more detail on that. And I don't want to speculate on the tidal surge that would arrive there.
Yeah, if I remember correctly, it's maybe a few feet.
Yeah, maybe 3 feet. But yeah, there's a great tsunami video, and they simulate a tsunami entering into the sound and then how it would bounce around, and it would last several hours, being that it's bouncing around, and it takes quite a long time to make its way with the fingers of the sound, but it's different for each area. So go to their website and click on that tsunamis panel, and the video should be in there.
I think Scott's gonna have to let us know what it feels like.
Yeah. Tsunami will be intense. If you live on the Sound, yeah, you could expect a big wave. But the lakes will probably have a seiche, which is kind of standing waves or waves created by the shorelines moving back and forth. So all the lakes around the area will have waves in them as well. Not a
model with it, and get yourself a little bucket.
Yeah.
Put a little boat on it. And see what happens.
Let us know. I think we're at the end of the list.
Yes.
You two are wonderful. Thank you. Thank you so much. So we've got time. Anne, do you want to introduce a couple of polling questions? So folks, if you are so inclined, feel free to take a bio break. Our next guest speaker will be starting at 11:30, but in the meantime, we've got a few poll questions that you can answer as they pop up. Yeah, okay. So feel free to take a bio break, and as the poll questions pop up, we'd love to have your engagement with it.
Thanks very much.
Thanks, doctors.